Exclusive disjunction or exclusive OR is a logical operation that outputs true whenever both inputs differ. It is symbolized by the prefix operator J and by the infix operators XOR, EOR, EXOR, #, a registered trademark, and a per-mil cent. The opposite of XOR is logical biconditional, which outputs true whenever both inputs are the same. It gains the name exclusive OR, because the meaning of OR is ambiguous when both operands are true. Exclusive OR excludes that case. This is sometimes thought of as one or the other but not both. This could be written as A or B but not A and B. More generally, XOR is true whenever an odd number of inputs is true. A chain of XOR XOR B XOR C XOR DA is true whenever an odd number of the inputs are true and is false whenever an even number of inputs are true. Truth table. The truth table of A XOR B shows that it outputs true whenever the inputs differ. Equivalences, elimination, and introduction. Exclusive disjunction essentially means either one, but not both. In other words, if and only if one is true, the other cannot be true. For example, one of the two horses will win the race, but not both of them. The exclusive disjunction, or JPQ, can be expressed in terms of the logical conjunction, the disjunction, and the negation as follows. The exclusive disjunction can also be expressed in the following way. This representation of XOR may be found useful when constructing a circuit or network, because it has only one operation and small number of AND operations. The proof of this identity is given below. It is sometimes useful to write in the following way. This equivalence can be established by applying De Morgan's laws twice to the fourth line of the above proof. The exclusive OR is also equivalent to the negation of a logical biconditional, by the rules of material implication and material equivalence. In summary, we have, in mathematical and in engineering notation, relation to modern algebra. Although the operators and are very useful in logic systems, they fail a more generalizable structure in the following way: the systems and are monoids. This unfortunately prevents the combination of these two systems into larger structures, such as a mathematical ring. However, the system using exclusive OR is an abelian group. The combination of operators and over elements produce the well-known field. This field can represent any logic obtainable with the system and has the added benefit of the arsenal of algebraic analysis tools for fields. More specifically, if one associates with 0 and with 1, one can interpret the logical AND operation as multiplication on and the XOR operation as addition on. Using this basis to describe a Boolean system is referred to as algebraic normal form, exclusive, or in English, the Oxford English Dictionary explains, either. Or as follows: the primary function of either, etc., is to emphasize the perfect indifference of the two things or courses. A. But a secondary function is to emphasize the mutual exclusiveness, equals either of the two, but not both. The exclusive OR explicitly states one or the other, but not neither nor both. However, the mapping correspondence between formal Boolean operators and natural language conjunctions is far from simple or one-to-one, and has been studied for decades in linguistics and analytic philosophy. Following this kind of common-sense intuition about OR, it is sometimes argued that in many natural languages, English included, the word OR has an exclusive sense. The exclusive disjunction of a pair of propositions is supposed to mean that P is true or Q is true, but not both. For example, it might be argued that the normal intention of a statement like "you may have coffee," or "you may have tea" is to stipulate that exactly one of the conditions can be true. Certainly under some circumstances a sentence like this example should be taken as forbidding the possibility of one's accepting both options. Even so, there is good reason to suppose that this sort of sentence is not disjunctive at all. If all we know about some disjunction is that it is true overall, we cannot be sure that either of his disjuncts is true. For example, if a woman has been told that her friend is either at the snack bar or on the tennis court, she cannot validly infer that he is on the tennis court. But if her waiter tells her that she may have coffee or she may have tea, she can validly infer that she may have tea. Nothing classically thought of as a disjunction has this property. This is so even given that she might reasonably take her waiter as having denied her the possibility of having both coffee and tea. Note: if the waiter intends that choosing neither tea nor coffee is an option, that is ordering nothing, the appropriate operator is NAND, PNANDQ. In English, the construct, either or, is usually used to indicate exclusive or generally used for inclusive. But in Spanish, the word o can be used in the form POQ or the form OPOQ. Some may contend that any binary or other n are exclusive, or is true if and only if it has an odd number of true inputs, and that there is no conjunction in English that has this general property. For example, Barrett and Stenner contend in the 1971 article The Myth of the Exclusive OR, 116-121, that no author has produced an example of an English OR sentence that appears to be false because both of its inputs are true, and brush off OR sentences such as the light bulb is either on or off as reflecting particular facts about the world rather than the nature of the word, or. However, the barber paradox everybody in town shaves himself or is shaved by the barber, who shaves the barber, would not be paradoxical if, or could not be exclusive. Whether these examples can be considered natural language is another question. Certainly when one sees a menu stating lunch special, sandwich and soup or salad according to common usage in the restaurant trade, one would not expect to be permitted to order both soup and salad. Nor would one expect to order neither soup nor salad, because that belies the nature of the special, that ordering the two items together is cheaper than ordering them à la carte. Similarly, a lunch special consisting of one meat, French fries or mashed potatoes and vegetable would consist of 3 items, only one of which would be a form of potato. If one wanted to have meat and both kinds of potatoes, one would ask if it were possible to substitute a second order of potatoes for the vegetable. And, one would not expect to be permitted to have both types of potato in vegetable, because the result would be a vegetable plate rather than a meat plate. Alternative symbols. The symbol used for exclusive disjunction varies from one field of application to the next, and even depends on the properties being emphasized in a given context of discussion. In addition to the abbreviation EXOR, any of the following symbols may also be seen: A plus sign. This makes sense mathematically because exclusive disjunction corresponds to addition modulo 2, which has the following addition table, clearly isomorphic to the one above. The use of the plus sign has the added advantage that all of the ordinary algebraic properties of mathematical rings and fields can be used without further ado. However, the plus sign is also used for inclusive disjunction in some notation systems. A plus sign that is modified in some way, such as being encircled. This usage faces the objection that this same symbol is already used in mathematics for the direct sum of algebraic structures. A prefix J, as in JPQ. An inclusive disjunction symbol that is modified in some way, such as being underlined or with dot above. In several programming languages, such as C, C++, C, Java, Perl, Ruby, and Python, a caret is used to denote the bitwise EXOR operator. This is not used outside of programming contexts because it is too easily confused with other uses of the caret. The symbol, sometimes written as or as. In IEC symbology, an exclusive OR is marked equals 1. Properties: commutativity, yes; associativity, yes; distributivity. The exclusive OR doesn't distribute over any binary function, but logical conjunction distributes over exclusive OR. Conjunction and exclusive OR form the multiplication and addition operations of a field GF, and as in any field they obey the distributive law. Idempotency, no; monotonicity, no; truth-preserving, no; when all inputs are true, the outputs is not true. Falsehood-preserving, yes; when all inputs are false, the output is false. Walsh spectrum, nonlinearity, 0. If using binary values for true and false, then exclusive OR works exactly like addition modulo 2. Computer science. Bitwise operation. Exclusive disjunction is often used for bitwise operations. Examples: 1 XOR 1 equals 0, 1 XOR 0 equals 1, 0 XOR 1 equals 1, zeros or 0 equals 0, 11 tens or 1001 equals 0111, as noted above. Since exclusive disjunction is identical to addition modulo 2, the bitewise exclusive disjunction of two n-bit strings is identical to the standard vector of addition in the vector space. In computer science, exclusive disjunction has several uses. It tells whether two bits are unequal. It is an optional bit flipper. It tells whether there is an odd number of 1 bits. In logical circuits, a simple adder can be made with an EXOR gate to add the numbers, and a series of AND, OR and NOT gates to create the carry output. On some computer architectures, it is more efficient to store a 0 in a register by XORing the register with itself instead of loading and storing the value 0. In simple threshold-activated neural networks, modeling the XOR function requires a second layer because XOR is not a linearly separable function. Exclusive OR is sometimes used as a simple mixing function in cryptography, for example, with one-time pad or faster network systems. Similarly, EXOR can be used in generating entropy pools for hardware random number generators. The EXOR operation preserves randomness, meaning that a random bit XORed with a non-random bit will result in a random bit. Multiple sources of potentially random data can be combined using EXOR, and the unpredictability of the output is guaranteed to be at least as good as the best individual source. EXOR is used in RAID 3/6 for creating parity information. For example, RAID can backup bytes 10,011,100 and 011011100 from two hard drives by XORing the just mentioned bytes, resulting in and writing it to another drive. Under this method, if any one of the three hard drives are lost, the lost byte can be recreated by XORing bytes from the remaining drives. For instance, if the drive containing 011011100 is lost, 10,011,100 and 11,110,000 can be XORed to recover the lost byte. EXOR is also used to detect an overflow in the result of a signed binary arithmetic operation. If the leftmost retained bit of the result is not the same as the infinite number of digits to the left, then the means overflow occurred. XORing those two bits will give a 1 if there is an overflow. EXOR can be used to swap two numeric variables in computers, using the EXOR swap algorithm. However, this is regarded as more of a curiosity and not encouraged in practice. In computer graphics, EXOR-based drawing methods are often used to manage such items as bounding boxes and cursors on systems without alpha channels or overlay planes. Encodings, apart from the obvious ASCII codes, the operator is encoded at U+22BB-XOR and U+2295-circled plus, both in block mathematical operators. See also, notes, or, CONJ22 Oxford English Dictionary, 2nd edition. OED Online. Davis, Robert B. Exclusive OR and Hardware Random Number Generators. Retrieved August 28, 2013. External links. An example of EXOR being used in cryptography.